Hello everyone, and welcome to today's presentation. Today, we are diving into a new paradigm for artificial intelligence in software engineering, titled Scaling Coding Agents via Atomic Skills. Building complex AI coding capabilities isn't about tackling a massive monolith all at once, it's about breaking problems down into fundamental, interlocking building blocks, which we call atomic skills. Let's talk about the problem we are facing today. Current AI coding agents are mostly trained to solve composite tasks, like end-to-end bug fixing. However, this composite task optimization hits a generalization wall. As the chart shows, if you use reinforcement learning solely on a bug-fixing task, the model becomes a brittle specialist. It completely fails to transfer its capabilities to out-of-distribution workflows like code refactoring, resulting in negative performance. Why does this happen? In the status quo pipeline, optimizing for a high-level goal using only sparse rewards, like getting a simple pass or fail on a test suite, forces the model to memorize task-specific heuristics. Because real-world tasks are infinitely diverse, this makes dense reward modeling intractable. Our proposed solution is the illuminated atomic pipeline. By breaking the black box open into fundamental steps, we can apply dense, execution-grounded rewards at every stage, learning robust problem-solving capabilities. This brings us to the core of our approach, the paradigm shift. Instead of training agents to solve specific, highly complex tasks like bug fixing, which we've proven is not generalizable, we train them to master the atomic building blocks required to solve any task. When an agent masters basic steps like code editing, review, and issue reproduction, it can naturally compose them to solve completely new challenges, like code refactoring, in a highly generalizable way. So, what are these building blocks? We introduced the 5 basis vectors of code generation. These are the 5 atomic skills we abstracted from real-world workflows. Code localization, identifying the exact files relevant to an issue. Code editing, generating precise patches based on explicit instructions. Unit test generation, writing tests that validate correctness and catch semantic edge cases. Issue reproduction, constructing minimal executable scripts to reliably trigger reported failures. Code review, reasoning about semantic correctness to judge if a pull request resolves an issue. To ensure these skills work seamlessly, they are built on the 3 pillars of atomic skill design. First, precise specification. The skill must be minimal and self-contained with strictly defined inputs and outputs. Second, independent evaluability. It must be automatically verifiable in a sandboxed environment with zero ambiguity and no partial credit. And third, reusable composability. The skill must serve as a universal building block that frequently recurs across high-level workflows. We look at how we evaluate the agent using execution-grounded reward logic. We do not rely on LLM vibes or partial text matching. For localization, the agent gets a +1 reward only if its predicted file set exactly matches the ground truth patch set. For editing, all unit and regression tests must pass. For testing, generated tests must pass on golden code and fail on mutated bugs. Reproduction requires logs to show failure before a patch and success after. And for review, the agent's binary judgment must match the ground truth label. We train the model using our joint reinforcement learning architecture. We use an algorithm called Group-Based Relative Policy Optimization, or GRPO. Tasks are sampled from a unified skills buffer and fed into an agentic rollout worker environment. The optimizer then updates a single, shared policy. Normalizing rewards across these candidate groups mitigates scale mismatch and encourages the emergence of shared representations for code understanding and tool usage. To run this at scale, we developed the ephemeral sandboxed infrastructure. Deployed on Kubernetes clusters, it supports over 10,000 concurrent sandboxes using 25,000 pre-built Docker images. To prevent execution bottlenecks, we decoupled rollout generation, the asynchronous data collection, from the trainer workers. We also utilize minimal tool scaffolding, restricting the action space to just basic deterministic tools like bash and str_replace to stabilize the reinforcement learning. Does this work? Absolutely. The charts show consistent mastery across the atomic foundation. Compared to our supervised fine-tuning baseline, our joint RL approach improved performance across all 5 skills simultaneously: localization, editing, testing, reproduction, and review. The key takeaway here is that joint RL optimizes these heterogeneous capabilities under a single shared policy without any negative interference, pushing average performance from about 51.7% to over 60%. But the real magic is compositional generalization to unseen tasks. By mastering reusable basis vectors, the agent naturally composed solutions for complex workflows it was never explicitly trained to optimize. We saw a 15.3% lift on the SWE-bench Verified bug-fixing benchmark, and a massive 29.6% lift on SWE-bench Multilingual. It also achieved solid performance lifts on terminal bench, code refactoring, and SWE-bench security tasks. Generalization is no longer brittle. The trade-off matrix breaks down the comparison. If we look at the middle columns, specializing an agent solely on editing or solely on bug fixing achieves good target task performance, but fails miserably at cross-capability transfer to other atomic skills or out-of-distribution tasks. Conversely, our joint atomic skills RL achieves balanced, sweeping improvements across target tasks, non-target skills, and unseen composite tasks alike. We track how the agent actually learns to behave over time, specifically looking at the evolution of tool use. We mapped out 3 distinct phases during RL iterations. In Phase 1, exploration, the step counts rise sharply as the agent learns to proactively use tools to gather context. In Phase 2, efficiency, the step count drops as the shared policy optimizes and discards inefficient tool sequences. Finally, in Phase 3, refinement, step counts slightly increase again as the agent learns to perform deeper, more rigorous verifications before submitting final outputs. We are moving away from the composite task paradigm, which relied on sparse binary endpoints, brittle heuristics, and intractable modeling, and embracing the atomic skill paradigm. This new paradigm utilizes dense, execution-grounded milestones, highly scalable reusable skill buffers, and produces robust cross-domain compositional transfer. We conclude that the future of coding agents is modular. We leave you with 3 main takeaways. First, deconstruct to scale. Complex workflows must be dismantled into independently evaluable basis vectors. Second, escape the black box. Execution-grounded rewards for atomic actions yield vastly superior capabilities. Third, mastery yields generalization. Joint RL on fundamental skills prevents negative interference, resulting in an 18.7% average performance lift across both seen skills and completely unseen composite tasks. Thank you for watching, and we look forward to a modular future in AI software engineering.